So what does it say?
Checking if it's true or not. You really are allowed to.
But at least no, but people heard about it, yes. And you never heard about it. See?
Okay, and apparently it's not true.
It's not true. Nobody said it.
I mean, they checked and they say it's not true.
You always learn. Maybe now at my age I can start. Drink water when I eat water. What the time is it, 2? Yeah? Everybody has like these atomic clocks, right? They do it here in Boulder, right? The most precise, right? So based on the Boulder time, can we start? What do you think? This old-fashioned. Yes? Okay. Okay, let's start with some announcement. So, I must say thank you for Yuval. And Yuval is arranging a water polo, I think called scrimmage in American English, right? Tonight. We don't know if they let us put the ball in the water, but Yuval is working on it. But the idea is 6:45 at the gym, or if you are like me and don't know the way, let's meet at 6:30 and we walk slowly with Yuval, because he cannot walk fast. We walk slowly with Yuval to the gym, and hopefully we can play some water polo. Okay? I mean, I've been playing water polo, well, not all my life, but roughly since I remember myself. I'd be happy to teach you something more practical than physics. But, so that's one thing. Let's go one thing. Second thing I wanted to, so I put some numbers up there. And there's one question that I got really confused today, and I don't really know the answer. And I was Googling it, but I didn't have enough time. So do you see those numbers up here? Right? They're all roughly about 558, 548, 550, something like this, okay? And I tell you so today is the longest day of the year. Everybody knows this, right? And that means that today, at some point during today, the sun was the farther away, well, from the Earth, or the other way around, the Earth, the distance, R1 minus R2 was the largest, right? That's only for physicists you can explain it like this, right? So we were actually in the farther away part. And then you go to the internet and you find the table of when it is every day. So actually, this year it's happened last night. So last night was actually the exact point that the sun was farther away. So I just look at this table, and you want to see how far away it's from year to year. So we all know that to a good approximation, a year is 365 days. And about a quarter, and about 6 more hours, right? So every 4 years we have this leap year. And you know the story that every 4 years you have a leap year, and then every 100 years you have an extra leap year, and then every 100 years you don't have the leap year, and every 400 you still have the leap year, right? So we know that it is about 6 hours, but not exactly, okay? So I looked it up, and I said, well, that's the 6 hours that you see, okay? So going from 2010 to 2011, the 1 year was 365 days, 5 hours and 48 minutes. And then going from 2001 to 2012, it was 3 plus 553, 555, 447, 447, 556, 550, and 5. And you can keep going. I just didn't copy it because I didn't have enough things. And I looked at this data. It was early in the morning before the hike. But I was a little confused. A year should be the same every year, right? We shouldn't have a difference of 5 minutes or 10 minutes. So first of all, I'm so amazed that they know it to such precision. I guess they know it to even better precision. It's really impressive, right? How people can do it. And then I saw why it is not constant. Why the difference is not constant. It must be gravity, right? Actually, I thought about the dark photon, but so what is it? What is it that is? No. That's the difference between the point that we are farther away from the sun. So if you you can define a year from when you start from the farther away point until you come back. That's the year, right? So in the ideal Kepler problem that we learn, I don't know, in your whatever, sometimes in your undergrad days, you remember we solved the Kepler problem. The Kepler problem, we had an ellipse, and the and we had whatever the time was the same. And here,
because we're not moving around the center of the sun, but points might be no, and then the other planets also changes.
Other planets. But I mean, the fact that we don't around the sun, that's of course, we reduced the two-body problem to a one-body problem, reduced mass, all this. So that's what I was thinking. What do you think? You think that's the right solution? This perturbation theory from Jupiter. What do you think? What about the moon? I would. Should or should not? It can be a huge effect, right? Because if the moon is here versus the moon is there, does it make it?
Actually, maybe, yeah.
Yes. Yes, maybe that is. But is the moon, I didn't think about it. Can the moon affect it or not? Isn't really what we are really measuring is the Earth-Moon system around the sun? Doesn't we really? So that's some internal motion of our. So we take the center of mass of the Earth-Moon system. And, anyway, so I didn't have too much time to think about it because I was preparing the lecture the rest of my day today. But probably someone knows the answer. And my feeling, it must be perturbation theory and must be the other planets. Okay, it must be. The precession of? So that's I was also thinking, it's the famous perihelion shift of Mercury that everybody know that was the check of GR, right? And we know that most of the perihelion shift of Mercury come from the other planet, and only about 10% of it come from general relativity, right? But even if you have perihelion shift, it doesn't affect the period, right? So if you just take the standard perihelion shift of Mercury, the perihelium change, so you kind of have an ellipse that rotates, but still the period is still a constant. So it might be some higher order effect. I don't know what. I mean, I'd be happy. I'm still here tomorrow morning if someone finds it. I don't know if you have an idea. Or maybe I will find it in Google at the end. Because Google have almost everything. Okay, so that was all the non-flavor stuff. And now let's come back to why we are actually here. And so in my first two lectures, I discussed flavor physics in the standard model. And today I want to start and talk about how we do, why we care about flavor beyond the standard model. And before I get into those things, I put this table up here. And this table, what I put is the bound that we get from meson mixing on some very generic dimension 4 operator. For example, the Keon system gives us a bound on the SD bar squared operator. And the bound, if you look at the real part of this operator, the bound is 2 times 10 to the 4 TeV. And the bound on the imaginary part is 3 times 10 to the 5 TeV. You remember in my first lecture I said flavor bounds are roughly 10 to the 8 GeV. That's where this number comes from the Keon. And we see D, B, and B sub S. And I guess you can see some pattern here. What kind of patterns do you see? So the bound on the imaginary part is always stronger than the bound on the real part. Okay? And kind of knowing the standard model, we understand where it's coming from because CP violation is somewhat small. And the other thing that we see is that, if you like, the lightest mesons give us better bounds than the heavier mesons. Okay? Do you see this? Okay? So I want just put out the number, remember some pattern, and then we'll understand a little bit how it is relevant to the, yes?
So those are bounds coming from oscillation, meson oscillation?
Yes.
How are the bounds on flavor changing neutral currents?
So meson oscillation is a flavor changing neutral current process. Yes. And I guess what you are asking, what are the bounds from things that violate flavor by 1 unit? So these are what we call delta F equal 2 operators because they violate flavor going from K to K bar. But the question, what can you get, for example, from B going to S gamma? Okay? And the answer is that that these numbers are also around. And in general, the bounds that you get from decays are weaker than the bound that you get from meson mixing. Meson mixing give you the strongest bound. Okay? But they are not much different. I mean, they are not that the bounds are completely useless or irrelevant. And also, I didn't really say there's different operators here. I didn't put the Dirac structure of the operators. The different Dirac structure you get, there's much more to it. I just gave the big thing. Okay? Good. So now come the big questions. Of course, we want to go beyond the standard model. And the question is why? Like why you want to do BSM. And I guess, I talked to some of you, I guess that almost all of you are doing BSM, right? How many of you only do standard model physics? Psh, yeah, I'm so happy. One. So why all the rest of you not join here and just do standard model physics? Let me tell you why you should do standard model physics. Because the standard model is the best theory ever invented. We as human beings were able, with very simple axiom, to explain everything we see. Every experimental result, this huge PDG book that you still can see, you can still buy it for free at CERN, right? All results are explained there. So you have a theory, you have the triumph, the biggest triumph of humankind in terms of our understanding of science is the standard model. And then we come here, all of us, just in order to say no. And you know how it is. Like the 750 go where it's like, standard model again. I don't want to do it, right? So why are we looking beyond the standard model? Now seriously, what are the reasons why we all want to extend the standard model? Why are we going to do physics beyond the standard model? Evidence? Let me start writing. I don't have a list. I count on you, guys. Dark matter, very nice. Of course, you know, that's the astronomer, that's cosmology, astro. It's not particle physics, but okay. No. Okay, it's important. Dark matter. Yeah. Number 2, why else? Neutrino masses. That's really important because they are really particle physics, but we solve it. We just put dimension 5 operator, we know what to do, right? That's simple. Okay, we don't need like whatever, 59 people here working on BSM physics, right? The hierarchy problem, that's I love, right? The hierarchy problem, go under the name of HP, right? And what is the hierarchy problem? It's completely numerical things, right? Where we talked about numerics today, right? Remember we talked about numerics? Okay, so we have a hierarchy problem. What the big deal? We just have some number, whatever, 10 to the minus 17 or 10 to the minus 30, whatever you want to call it. Okay, but it's still, the data is explained. It's completely our own, whatever, ignorance of what beauty is. Because we think that all the one numbers are nice and 10 to the minus 17 is not nice. You know, be a little more open-minded. 10 to the minus 17 are as nice as 1. Okay, what else? Okay, mu on g minus 2, let me put it into a very big thing. We have experimental deviation from the standard model. So mu on g minus 2, whatever, 3 point, how much, do you remember? 3 point, yeah. B2k pi is 3.4, and I can actually, I don't remember all of them. We have quite a lot of those 3 point something sigma that are, yeah, even the forward backward asymmetry. Experimental, you know, we have this huge book, and you find whatever, 15 3 sigma effects. Shouldn't be a big deal, right? I mean, you should actually, if we didn't have any 3 sigma effect in this big book, that will be a statistical anomaly. The fact that we have some 3 sigma. So, experimental data, I don't buy it. The strong CP problem. Theta QCD. So theta QCD, what is the big deal? The big deal is that we have a parameter in the standard model that it should be 10 to the minus 10 or smaller. So what? The cosmological constant. So you want to bring smaller and smaller number, okay? I want to bring 10 to the minus, okay, let's do 6 cosmological constant. Now we go, right, 10 to the minus 10, 10 to the minus 20, 10 to the minus 120. Anybody have a smaller number? I can come with a smaller number. Inflation. But that's also, yeah, inflation. You know, those two definitely has something to do with gravity that is completely not in the standard model. That probably should be the number one answers, like we don't have a quantum gravity. So clearly the standard model has to be explained because of quantum gravity. So let me add my own quantum gravity. Okay? Fermion masses are all over the place. in particular when you take the log of them, right? If you don't take the log of them, all of them are small except one, right? So the log of the fermion masses are all over the place, okay? So let me call it MF. But MF is the same story. Like within the way we built, what was our working assumption, how we start doing model building? We just say, you tell me the symmetry, you tell me the representation, the spontaneous symmetry breaking pattern, and then you write the most general renormalizable Lagrangian, you remember? And then you measure the parameter. So the fact that the mass of the fermion are completely doesn't look natural to you, it's completely within our rules of the game. We set the rules, right? And the rules works extremely well. Just happen that the masses are not what you expect. And where do your expectations are coming from? Why would you think, oh, the masses should be all the one? Because we saw the top quark? I mean, no, why? Why we had this, right? It's somehow internal to us. Yes? Biogenesis, that's a big deal. Biogenesis, of course, we want a universe that have baryon in it. And of course, this has to do with a lot of cosmology that we also don't understand. Okay? So I know I kind of make fun out of this, but the truth is that the reason that we believe there's something beyond the standard model is just because we see all those kind of hints that there's something deeper. Okay? There are small numbers, and we said maybe there's something deeper about this small number. Maybe we can understand this small number. There's some experimental data like biogenesis that we don't really know what we are, what we have. Okay? Definitely dark matter we don't fully understand. We have experimental data. That's the one that we really have. However, almost all of us, including myself, most of what we are doing is related to this one problem. No, you disagree? Yeah, you do dark matter. That's fine. Yes, you're right. Yeah. So since I own you, let's do both, right? But really, most of us, if you like, I wouldn't say most of us, but I think that in terms of our field, particle physics field, this is the question that drives the field in the last, 20, 30 years. Definitely when I started doing physics, it was already kind of the number one question. Of course, we ask other questions, but it is the hierarchy problem. And one reason that we really like the hierarchy problem is the following things. I assume that you heard the following statement, that if we ask what's happening about fermion masses, we ask, fermion masses is not a problem because it's technically natural. However, the hierarchy problem is a big problem because it's not technically natural, right? So what is the big deal? Why do I care if it's technically natural or not? Okay? And let me tell you my answer to this, and people have different answers. For me, the big difference between technically natural and not technically natural hierarchy problems are the following. If I have something that is technically natural, the solution can live very up there at the Planck scale. And then we cannot probe it, so I don't care about it. Okay? In everyday language, we sweep it under the rug. Okay? We just said, yeah, now put it there at the Planck scale, so I don't care, right? It's someone else's problem, right? It's those, the new tenant that will come. They will find it there, okay? But hierarchy problems that are not technically natural, I cannot do it. Because the hierarchy problem, the solution has to be at the TeV scale, right? And therefore we say, let's build this, collider, and if this collider doesn't find one, let's build a bigger one in China, etc., and we find it eventually. Because we know that if the hierarchy problem has something to do with nature, it has to be done at the weak scale. While the fermion masses, which is a technically natural problem, doesn't have to be at the weak scale. Okay? So that's why we got excited about the hierarchy problem, because we hope that we get something at the weak scale. Something that is not technically natural comes with a scale associated with it. A technically natural problem doesn't come with a scale, and therefore you don't really know where you can solve it. Okay? Good. So what I want to do in this lecture, I want to make the assumption that we try to solve the hierarchy problem. Therefore, we try to put some new physics at the TeV. And the question is, when I put some new physics at the TeV, how flavor actually affect my model building techniques, okay? And naively, you should say it's a very big deal. Why? Because the hierarchy problem points into a scale. What is the scale? It's 1 TeV. Then you look at this table above, and you see that the bounds from flavor are much above 1 TeV. Therefore, you cannot put a new physics at the TeV, right? That's the naive solution. But you say, well, but I still want to do it, okay? So what do you have to do? You have to use some model building tricks in order to make these bounds not affect the hierarchy problem, okay? This bound make under the assumption that the coefficient is order 1, and therefore you have whatever, SD squared operator over lambda squared, and that's how you put the bound on lambda. But if you are smart and you use some model building trick, you can put that the number is actually much smaller before the scale, and it's actually agree with the hierarchy problem, okay? So when you do model building, the trick is always the same. Is how we put some non-trivial flavor structure such that we can accommodate this flavor bound. Okay? If you like, the answer is as following. Whenever you do model building, you must do some tricks in order to make sure that this is okay. Yes? Good. So I want to discuss some of these tricks and how we are dealing with it. Okay? And so in general, I would say there's 5 types of tricks that we are using, and all the tricks on the market are some kind of combination of those 5 tricks, okay? And many times you have to use many tricks, okay? Because you say, oh, this trick gives me 1 order of magnitude, this trick 1 order, this one gives me another 2 orders, and at the end I can get whatever the 5 or 6 or 7 order of magnitude that I need, okay? And I might be wrong, actually, and maybe there's some tricks that I'm not aware of that doesn't fall into these 5 classes, but I think that it does, and if you have, we can discuss it later. So here are my 5 tools of how to actually make flavor bound disappears, okay? So number 1, when we talk about it, was it over dinner yesterday? That's how we learned to write letters like 1, 2, 3, and I said, no, I don't do it anymore, right? Oh, no, it was over breakfast. And I said, no, I don't, but now you see all my 1, 2, 3, 1, 2, 3. So bad. Anyway, what are the 5 tools? The first one is to go to one loop, or actually some loops. So somehow you made your physics go into higher loop than new physics. The other one is to have a new physics. Number 3 is universality. Number 4 is alignment. And number 5 is discrete symmetry, in particular CP symmetry. Okay? So basically, these are the tools, and here it's not really the tool, it's just ideas of what tools we can use. And I'm going to say how we actually can use this kind of ideas in order to help us to get away with flavor bounds. And we kind of saw many of those already, right? So let me try to discuss one after another. So the first one is rather simple, is to think that I want to put my new physics in loop. So clearly, if you say, oh, I have some new operator, and this operator is a 3-level operator, if I can impose some symmetry, that I put it into one loop, right? So when I put it in one loop, I gain whatever a factor of 100 in my amplitude. Yes, this 1/16 pi squared. So do you have ideas how, if you have some in general model, how you take your new physics and put it in the loop? How do you do this? That's right, but how do you make it? How do you actually, so I said, you write your most general Lagrangian and you find that there's some new thing that you can, with some new physics, you can mediate FCNC at 3-level. What would you do, say, oh, I don't like it at 3-level, I want to make it into one loop. What kind of tools do you have? Yes. Usually, it's some kind of a Z2 symmetry, okay? So if you impose some kind of Z2 symmetry, many times you can say, oh, when I impose a Z2 symmetry, what does it make for your new particles? Your new particles have to be produced always in pair. In any vertex, there should be 2 of them, okay? So if there should be 2 of them, they cannot be a 3-level amplitude. You should close the loop, okay? And you can come up with name for those symmetries. They always come with some letter, right? Like R parity, T parity, K parity, okay? Is there more that I forgot? U, no. U parity, no? Right? So that's how we do it. We impose a Z2 symmetry and we do it. Also, sometimes we can actually use fermions. If we can change. Fermions also must be produced in pairs. So if your heavy physics is fermionic, you also cannot have them going in 3-level. It's the same idea. What's Z2 symmetry we use for fermions? It's not really a Z2, but what symmetry it is? angular momentum, basically, right? The fact that we cannot produce, that fermion has to be produced in pairs. Okay? So it's the same idea. You impose a symmetry, and many times this symmetry, you say it's exact in my theory. Okay? So that's how we put things into the one loop. It's the same. Within our model building tools, we have this. We put things in loop by imposing some Z2 symmetry. Okay? Yes? That's right. So, yeah. So many times you say, oh, the point is, what do you want? So why do you start to do model building? You start to do model building in order to solve the hierarchy problem. So you said, in order to solve the hierarchy problem, what do I need? Oh, I should have said it before. In order to solve the standard problem, what do I need? The hierarchy problem, what do I need? I need a top partner, right? So the top partner can be bosonic or fermionic, right? So depend on your model. So sometimes your model tells you if it's bosonic or fermionic, okay? Just saying that if it's fermionic, you many times gain this one loop automatically. Not always. That's right. Of course, there's many. All I want to say, I'm not going to give you like specific model. It's just these ideas of how we do things, right? And we are all familiar with R parity, right? Everybody knows R parity. It's not. Okay, so that's the one loop. Number 2, heavy new physics. So that's a really cool idea, okay? The idea is the following. We have bounds. So if the bounds are such that are, all we need is to make the new physics heavy, let's make the new physics heavy, and then we don't have a problem. How do you like this solution? Yeah. Sometimes it's called, I learn all this expression that I want to use. It's called, you throw the baby with the bath water. How you call it? How you say it? How someone said in incorrect English? Yes, throw the baby with the bath water. Don't imagine it like you have yes. So of course I solved the problem, but I solved the flavor problem by completely not solving the hierarchy problem. Because why I wanted it to start? I wanted the idea to start because I want to solve the hierarchy problem. So I want new physics at the TV. And I said, but then I have problem with flavor. So let's make the new physics very high, and then I solve the problem of flavor. But then I don't. I have the hierarchy problem. Okay. So why it's still number 2 on my list? Because there's a little subtlety here, okay? For the hierarchy problem, what we really need to be at the TV? What particle? The top partners, right? So we need a TV top partner basically to solve the hierarchy problem, right? However, if you look at the flavor bounds, where are the stronger flavor bounds? They come from kaon and D physics, which are only the first 2 generations, right? So if I treat my generation very differently, if my new physics third generation is light, but my new physics first and second generation are heavy, I can actually, another expression that I know, you can eat the cake and keep it. How you say it? No. How you say it? Someone American. I need. How you say? Have your cake and eat it. Yes, so I can have my cake and eat it too, right? Because the top partner are light, and the charm and the U partner are heavy. Okay, so then I can satisfy those kaons, K and D bounds, but my problem of third generation are much weaker, right? Because the bound from B physics is a factor of 2 orders of magnitudes weaker than I have from the top. So it's not a complete solution, right? I cannot really use this as a complete solution, but it's helping, right? I do one loop, I gain another factor of 100. I do heavy new physics, I do this separation, I can gain another factor of 100. Okay? So these are the tricks that we are using. Of course, it can create a lot of problems because if you have complete if the new physics is very, very different, then you start asking the question why I have those different scales, and you produce new hierarchy problems into the game, etc., etc. And then what you do, you use more model building tricks in order to solve them, and that's how we do model building, right? And you can think about ideas how you can actually have the partners have an inverse hierarchy compared to the fermions. Anybody has an idea? You probably know the name. So what I'm telling you, I want the top partner to be light and the U partner to be heavy. So it's the inverse, right? The heavier fermions, their partner are light, and the light fermions, their partner are heavy. What kind of a mechanism? Do you know of a mechanism? The seesaw mechanism, that's why it's called a seesaw. Everybody know what a seesaw is? The top seesaw, yes. Right? That's the idea of a seesaw. The partner is heavier, so such you can say, oh, the product must be the same. Right? And you can do model building tricks by adding every. Okay? So all those model building tricks we have, and they are kind of come from those kind of idea. Okay, so we use number 2 in this list. Very good. Number 3, universality. We talked about universality already when we talked about the standard model, and we say that the reason that the Z doesn't have flavor change in its kind is because the coupling to the Z is universal in the standard model. And this idea of universality can help a lot when we have some new physics. In particular, if we have some, for example, new heavy degrees of freedom. But if these new heavy degrees of freedom, for example, are degenerate, and they are universal, they have universal mass, any flavor rotation on them will do nothing to them, right? So they will always be diagonal. Make sense? Because a unit matrix, no matter in what basis you look at them, it's always diagonal. So that's the idea of universality. That somehow, you just say that for some reason, the heavy partners that I put have universal coupling or universal masses, and I use this proportionality in order to solve the problem. Okay? The question is, in the model building question is, why do I have this universality? And then, you have to work out how I get a model that gives me universality. But the idea is to get universality. Okay? And probably within those, when people start looking beyond the standard model and start building a model beyond the standard model, that was kind of the only one that was kind of people were using. So in the early days of supersymmetry, how people solve the flavor problem, they make the assumption that all the squarks are degenerate. Okay? And if all the squarks are degenerate, they don't generate any flavor changing. Right? Just because you can rotate, it's the same thing. You have a unit matrix, no matter how you rotate them, stay the same. Okay? And this idea is still around. The question is how you make things degenerate. That's a deeper model building. In SUSY, how do we make sure that this is universal? How we did it in the past, we just said, oh, this has to do with SUSY breaking, so I don't care because I write an effective theory, so I don't know. And then people start studying models of spontaneous SUSY breaking, and then in all these models they come. So which, for example, some SUSY model that you know about that give you approximate universality? Gauge mediation. So gauge mediation, SUSY breaking give you flavor universality. Why? Because the masses are proportional to the gauge coupling, and the gauge coupling of the different fermions are the same, so therefore you get it. Okay? And it's approximate because the higher order correction, and there's some. Are we with universality? All okay? Good. Number 4, alignment. We also talked about alignment before. And the way we talked about alignment was when we talked about the Higgs, how the Higgs is not coupled to the standard model in a non-diagonal way. We use the same idea. That is, we put some new physics in, and this some new physics has some whatever matrix that couple to the standard model flavor of fermions. But for some reason, this matrix is actually aligned with the Yukawa coupling. Okay? So therefore, when I diagonalize the Yukawa, I also diagonalize these new things, and therefore I get also diagonal coupling there. It doesn't have to be universal. You see the difference. Here, the coupling is universal. Here, the coupling are non-universal, but just it's in the same basis where the Higgs is diagonal or where the masses are diagonal. Also, these coupling are diagonal. Okay? So that's again another idea that we can use. Any question on this? Looks simple, right? As long as you talk about ideas, then how to implement them. It's a whole different story. But the point is, when we understand what the ideas are, then we'll understand how we can actually go and implement those things.
So
yes.
we discussed how for example, have alignment quarks coupled to different mixes, they don't mix. HU.
Yeah. But I'm talking about alignment to coupling, for example, for the gluino. So in the Higgs, we get exact alignment in the MSSM. But the question is, can you actually get alignment for the coupling of the squarks to the gluino? Okay. So in general, the coupling of the gluino quark vertex is completely arbitrary. Okay. And the question, can you make this vertex to be the same as the quark gluon coupling or the Higgs. And I will give you I'm not sure if I have time, but I will mention some ideas how to get alignment in SUSY. Okay. Yes, I will talk about it. I will give some example in SUSY in whatever 10 minutes. And the number 5 idea is to use CP symmetry. So all those 4 ideas work both for the real and the imaginary part. The 5th part works basically only for the imaginary part. And the idea is, if for some reason we can assume that all the phases in the new physics model are just 0. Can you assume it? I mean, if you write the most general Lagrangian, you should not have, the phases should be order 1, right? So if I write my SUSY model, or whatever, RS model, or whatever you want, there should be a phase there. However, that's again another model building trick. You said, I assumed that in this sector, CP is conserved. And that's something that we have in our toolbox of model building. We say, I assume that here CP is conserved, and there CP is violated. Why CP is violated in the standard model but not in the new sector? We say, well, because this CP violation actually comes from some higher dimension operator in some way, and we can UV complete the model. Okay? And we do it a lot. We do it a lot by putting things and said, well, I don't try to solve the whole model. I have some effective theory. So within this effective theory, here I have CP conservation, here I don't, and I keep going. Okay? So these are the tools that we have. And as I said, many times we need some combination of those tools in order to go on and and keep doing it. Any question on this? Anybody feel I missed something? That you have a mechanism that you heard about, that you work that doesn't fit into those 5s? MFV. I will talk a little bit about MFV. I think MFV sits here. Where MFV sits? Alignment. I feel that MFV is an alignment. Those of you who doesn't know MFV, I will discuss it in a minute. But basically, the idea is that all flavor violations are proportional to the Yukawas. And that's an alignment mechanism. Because you somehow may say that everything is proportional to the same matrix. Right? So that's give you an alignment. Anybody else that... I've been thinking about it for, well, not for so long, but definitely for a few weeks about this list. And that's all I could come up with. No. So there's always this kind of say that, that's just cosmology puts you into where you are. But that's somehow, this anthropic whatever argument just say, yes, just the numbers are small just because. And, so it's not within our model building tools, right? We try to explain it based on some argument, right? Some symmetry, some reasons why these are so. Yes?
Locality. You put sequester.
Yes, so locality. So I'm actually going to discuss a little bit of RS flavor, right? So RS flavor solve this problem somewhat by locality, okay? And what do you get by locality? So locality does give you, what I think locality does for you. So depend where you put it. So if you put it far there, like in some UV brain, that's basically something like heavy new physics, right? And if you have things in the right.
But I mean, for example, in the gravity mediation, even if it's Planck suppressed, still you can get the flavor violation.
That's true.
Even when you really sequestering it, you don't get.
That's right. Yes, so but I think it's because the reason is that because it's heavy. So if you were put them far away, right. And actually you also have some kind of an alignment. So when you do RS, what they call RS gym, but is really an alignment mechanism. That's what I think, right? Yeah. Because you basically, because the different profiles of the fermions, they affect both the coupling to the KK mode and the coupling to the Z, and give you the mass. So that's kind of an alignment mechanism. Yeah. That's what, yes? Yes. Anyway, so I was thinking about it. It's definitely, I have no proof that that's all our tools. That's what I could come about, and I'd be happy to. Yeah. Okay, so I want to give you now some examples about MSSM. And that's always the first example that we are talking about. So we have these tools, and I want to get into some real models that people have been studying and see how these models actually use this kind of ideas to solve the flavor problem together with the hierarchy problem. So what is the problem in the MSSM? So the MSSM, everybody knows, right? It's really cool idea. You impose supersymmetry, everything is nice, and then all the problems are coming in the soft term, right? And the soft term, what do you have? You have huge number of A terms, soft masses, B term, whatever you want to have. You have huge number of the MSSM. The minimal version of the MSSM is go under the name of MSSM 124 because it has 124 parameters, right? Compared to 18, it's whatever factor of 10. So you kind of have this really cool idea of just imposing a symmetry, and then boom, you get another factor of 10 masses parameters, and that's after you impose the R parity, right? You got some SUSY lectures already, right? And I'm sure you kind of knew about the MSSM also a lot before. So I'm not going to describe the MSSM. I'm going to ask where are the flavor bounds coming from. So what are the problems in a generic MSSM? So in a generic MSSM, the squark masses are completely arbitrary. They have nothing to do with the A term are completely arbitrary. They have nothing to do with the Yukawa coupling. So of course, you already know the solutions, right? People said, oh, the A term are proportional to the Yukawa. Why? Just because. And the the squark masses are universal. Why? Just because. And let's go on, right? And that's how they did it in the 70s and 80s. That's how you start. When you have a new idea, you just put all these assumptions so you can start doing something. But now, 30 years later, of supersymmetry, we want to ask this question. But in general, you have an arbitrary mass matrix for the squarks, and then after you move to the mass basis of everything, like the squarks, the gluinos, etc., you have vertices like this, something like say UI square and a gluino, right? So you have a U gluino vertex, up gluino, and they are not, in general, they are not diagonal, okay? So I don't know even what does it mean to have a diagonal, just have some mass eigenstate, and the three quarks mass eigenstate couple, all of them couple for the three, or the six, whatever I didn't put the left and right, all the quarks eigenstate. There's huge flavor violation in these vertices, okay? And you have the similar vertices with the chargino and the neutralino, and you always have these things, okay? In general, that's what you have, okay? And that's going to give you a big problem. And on top of it, you also have CP violation problem in supersymmetry. Not only that the fact that these coupling are in general CP violating, in supersymmetry in general, you have flavor diagonal CP violating phases, okay? You can talk about the phase of the mu term, for example. It's a basis-dependent choice, okay? Or the phase of the A term. There's a basis-dependent choice. However, you actually have phases in the MSSM even if you didn't have if you have only one generation. So there was no question of flavor, you still would have CP violation. Okay? So the question, how do you solve this? Usually, how do you solve it in supersymmetry? You just assume that it's not there, right? But you want to do better, right? You just assume that it's CP symmetric to some reason and it's just not there. But you can do better with other tricks, okay? So let me discuss one particular bound that we can get, and I want to give you some ideas of how we do it, okay? So the best bound usually come from KK bar mixing. And if you do the calculation of KK bar mixing, you have again a box diagram. Oh, I should of course mention that in principle, if you don't have R parity, you have things at tree level. But usually you want R parity in order to solve proton decay. So we kind of piggy ride on proton decay that already impose R parity, and therefore everything is already at one loop. So at one loop, what diagram we get for KK bar mixing? We get this diagram. That's usually the dominant diagram, but there's many others diagrams. And this diagram has something like this: S, D bar, D, S bar, and here I have D tilde I, D tilde J, and here I have my two gluinos. Okay? What? Thank you. So what should I do? Should I change the lines or the labels? Labels? Lines? Okay. Labels. How I made this mistake? It's so bad. But that's why you know you can count on your students, right? You know that you make such a mistake. Gluino, DI, DJ. Very good. I don't know if very good, but that's what we have. So then you go and calculate this diagram. And what you find, I'm not going to do the full calculation, but we can estimate it quite nicely. We find that this diagram is roughly, let me do it like this. G strong over what? G strong to the 4 over whatever, 16 pi squared. Right? That's just the one loop. And then you have all these other factors. You have factors, if all those guys were degenerate, it would go to 0, just like the standard model that we did. Same story, so you must have some delta m squared squared. That's come from this degeneracy. And then just to make sure that the dimension is right, you have 1 over m squared squared. This may be a little bit surprising, because in the standard model we just make this argument that it go like the positive power of the mass, and here it's what we naively would think, that it's suppressed by the heavy guys. Does it make sense now that we have suppression by the mass of the heavy guys? Yes? Because it doesn't get mass from the X. Very good, right? That's what the point we made last time. This is the heavy scale. Okay? And then the last thing that we have, and not the last thing, we also have the mixing angles that come here into the game. So we also have times some mixing angles that I can call them K12 left times K12 right. Okay, there's some mixing angle that enter into the game. If the mixing angle were 0, of course, I would not have anything. That is, the mixing angle, if this di was just, if this vertex were flavor diagonal, that means that the mixing angle are 0, I will not get anything. And you have to be more careful about what mixing angle you are talking about, because you have quite a lot of guys floating around. In the standard model, it's easy. It's only the W coupling. In SUSY, you have many mixing angles, right? You have the mixing of the W, you have the mixing angle of the gluino, you have the mixing of the chargino, the neutralino, right? So depend what mixing angle you define. So here is the mixing angle between, in this vertex, the gluino, actually here I use up, but the down type, right? And then what is the last one? The last factor that I care about, because this diagram gives me KK bar mixing, and the strongest bound come from the imaginary part, so there's also a factor of delta, some delta, which is some CP violation phase. Okay? So if you say, oh, naively what I want my squarks to be the weak scale, but we know they are not, so now we all want them to be TV, right? So we want the squarks to be of order TV. This delta m squared naively is of order also TV, so that's roughly cancel. This mixing angle are naively order 1, and this phase is naively order 1. Okay? So when you plug this in and compare it to nature or compare it to the standard model, you get huge result. Because in the standard model, if you compare this result to the standard model, what in the standard model we have? Instead of G strong, we have G weak. So we're already losing something. Because instead of this delta m squared, we have MC squared, right? So this was much smaller. Okay? And this mixing angle was also very small. Okay? So in the standard model, it's a similar structure, but there's a lot of small numbers. In SUSY, naively in SUSY, there's no small numbers, and it's about 7 or 8 order of magnitude. I don't remember the number exactly, but much larger than what we see in nature. Yes? This is the mass difference between the different squarks. Okay, so you have, it's delta m. I do write too small. I should have tried. Delta m squark time 1 over m squark squared. Okay, so it's the delta m, just like mc squared minus mu squared that we have in the standard model. That's the sparks different that we have. Okay, and when we talk about flavor problem in SUSY, usually that's the biggest problem. Okay, when we solve this problem, all the others are kind of taken care of. Not always, but most of the time that's the biggest. Okay, so now of course, you know, when we say MSSM, yes. So epsilon, let's call it epsilon, right? So, of course, there's this, whatever, prop 2. And what I really mean is epsilon in front, okay? And you have to normalize it correctly. I also didn't really, there's also some, the SD squared, the operator itself, and there's some hadronic matrix element, etc. So there's more to what's going on. Yeah. Maybe the simpler way to do it is what I'm just asking. Let's ask the following question. What is the SUSY versus standard model? And then all the factors cancel, and then I'm just having this compared to the standard model one, right? And then it's a pure dimension. What I'm just saying is, there's more to it. Of course, this is not the full thing. Just trying to get you the fundamental thing what's happened. The fundamental thing is that you have the strong coupling, you have one loop, you have splitting, you have the heavy scale, you have the mixing angle, and you have the CP phase, okay? And it's correct. There's, you have to make sure that everything is fine, okay? So, how do you solve it, right? So, there's so many MSSM on the market. There's no one MSSM. Well, in the following sense, there's one MSSM in the sense that we have an A MSSM, N. We have an N MSSM, right? But there's no D MSSM, right? You have many, everybody have its own D MSSM with different value for the parameters. So how people have been tried to solve this problem, okay? Do you know about some ideas how people have been trying to solve this problem? I'm sure you read some papers about this. Yes? Degeneracy, for example. So how people they just said, well, let's assume that this delta n squared is 0 or very, very small. And how do you do this? You assume that for some reason this quark's mass matrix is degenerate. Okay? And for example, you can get it from gauge mediation, breaking to a good approximation, right? So that's one idea.
Didn't the stop and term will be the same time?
Almost. They will be approximate degeneracy, right?
You don't want that.
Why? So actually, it's quite good. If all the quarks were degenerate, I think we'll be really okay. It will solve the problem. It will solve the flavor problem, and it can solve the hierarchy problem at the same time. Okay? Another idea is to get this 1 over m, this is squared, by using heavy physics, right? So if I put I assume that for some reason I have approximate, the mixing angle are very small, and then I put my heavy guys to be light and my light guys to be heavy, the partner of the top to be light and the partner of the light guys, and I can get suppression from this part, okay? How can I make this K to be very small? Alignment, right? Then for some reason, I can have a mechanism that make this K to look very small. So if this K matrix is diagonal, is like the unit matrix, K12 is very, very small. Okay? And the last thing we can do, we can set delta to be small from the reason that I made. Okay? So basically, we just see that in supersymmetry, this kind of general thing that we have, you can use all of them. Okay? And hopefully I can give you some example, but probably I will run out of time. But I have one example of how to play the alignment trick, okay? And I'm not going to, I hope you kind of know a little bit about the gauge mediation and how you get it there, okay? Let's see. Let's talk about one more example. Let's talk about Randall Sunroom. So again, I assume that all of you know Randall Sunroom, right? Yes? Okay, let me plot a little Randall Sunroom thing. So you have the UV brain and the IR brain. And how do we play the flavor games in Randall Sunroom? So the way we play the flavor game is as following. So a little bit of a history. In the very first paper of Randall and Sundrew, they put everything in the IR brain, basically, and there was nothing in the bulk. And then if you put everything in the you have a huge flavor problem. Why you have a huge flavor problem? Because you can just write a higher dimension operator that are suppressed by 1 over TeV on the IR brain, and you have a problem. And then a few years later, people realize that what you want to do, you want to put the fermions in the bulk, and then, depend on the mass parameter in the 5-dimensional theory, the different zero modes have a different structure. Okay? So for example, that can be a UR, and that can be the CR, That will be the CR field, and that can be the TR field, right? And when you work it out, I mean, I'm not going to work it out for you. The very basic idea is as following: if the Higgs is on the IR brane, the Yukawa coupling is proportional to the overlap between the wave function of your field and where the Higgs is. Okay, so the more the field is more closer to the IR brane, this field has bigger mass, right? So you put the top such that you have higher overlap with the IR brane, so you get higher top mass, smaller charm mass, and even smaller U mass. Okay, so that's the idea. So it's kind of a cool idea. All you have to do is just you play with these numbers and you find these things. It's a really, really nice way to solve the MF, the mass problem, because you change your mass parameter by a little bit. The profile change in an exponential way. You just solve with some Bessel functions. You just solve those Bessel functions. This exponential change a little bit. Okay, and just by changing the exponent a little bit, the overlap changed very, very dramatically. Okay, so just by putting all the one numbers, you can get a huge hierarchy like you see in nature. Okay, yes. So what you do, you have to solve. So I'm not going into this, but the way you do it, you just said, "Oh, I take my five-dimensional fermionic field and I put it in the bulk, and then you have a mass parameter, a five-dimensional mass parameters. And when you change your mass parameters a little bit, you're going to see these kind of things, okay? And in whatever unit, it's in a half, when the mass is half, you get a flat profile, okay? And when the mass is less than a half, you get a T kind of profile. And when M is larger than a half in the correct unit, you get this kind of things. And then all you have to do is just say, "Oh, I want to make such profile that will fit the masses that I see." And the answer is that you have number between 0.4 and 0.7. Actually, it's kind of amazing that the number sits very, very localized around 0.5, and you basically explain it. And if you want to explain neutrino masses, this number goes to 1.1. Okay? So you just change the mass parameter very little because it's exponential. Okay? This is always the trick. Always the trick. Maybe I should mention it. How do we solve hierarchy problems many times? You said, it's not the physics is the log. You are wrong. You're talking about the wrong number. Just take the log and then it's easy, right? You see all those problems? You told me, it's the hierarchy problem. It's 10 to the 17. I said, take the log. It's 17. Theta QCD, take the log. It's 10. The cosmological constant, take the log. Let's take it twice, okay? So, it's already 10, right? So it's really, really, that's the idea, okay? The idea is how you can make a physics such that you argue that the physics itself is the log, okay? And actually, we know some hierarchy problems that we know how them solve, right? For example, radioactive decays. So if you look at radioactive decays, you should be extremely surprised on different lifetime, beta decays, right? You can have some particles that have beta lifetime of whatever, nanoseconds, and we know that we have other things that have lifetime of 10 to the 20 years. So how come beta decay, which is just the same thing, have a huge lifetime, or alpha decay, this spread of lifetimes? Well, because we understand the physics at the end of the day. If you think about the model of alpha decay, the model of alpha decay is tunneling. Right? And tunneling is exponential. If you make your barrier larger by 2, you just have much, much bigger because it's e to the length that you go under. You remember the WKB approximation? Remember those things, right? Yes. So that's what it is. You just take your potential and move it a little bit down. That's going to change the lifetime by huge numbers. Because what you do, you take advantage of exponents, right? Because you know that tunneling is an exponential phenomena. Okay, so that's one fine-tuning that nobody ever talked about. Why we never talk about the fine-tuning of radioactive decay? Because we solve it. How do we solve it? We understand that quantum mechanics, that the right number is not the lifetime, but the log of the lifetime. And then it's a solved problem. Okay, so that's what we try to do here. So this is an example of how we put everything in the exponent and get this kind of a structure. Okay. So that's really cool. It's Randall Sunroom is really, really a cool model. It's really do a lot of fun things for us. And in particular, when you put the things in the bulk, it also solves the mass fermion. But the question, how does it solve for us the flavor problem that I am talking about? And basically what it does for us, it does alignment for us. Why it does alignment? Because now I'm asking, let's say I have some KK excitation of whatever new particle that live here. Okay? So whatever new mediation of flavor that I can have are there. These new particles also couple to the fermions based on the same hierarchy, right? So I get kind of the same Yukawa coupling. So the same Yukawa coupling, the Yukawa coupling is determined by the profile of the zero modes. The profile of the zero mode basically is the same for any particle that is stuck to the brane. And if my new physics particle is not really stuck of the brane, it's have a little bit different profile, not like a delta function on the brane, but it's something like this. It's a little different, so I get an approximate alignment. But basically, I get alignment because the same physics that create the Yukawa coupling also create the coupling to the new degree of freedom. Okay? That's the alignment. Unfortunately, this mechanism got the name of RS-GIM. And if you read in the literature, it's RS-GIM. And why I say unfortunately? Because the GIM mechanism, it's which of the things on this list? The GIM mechanism used unitarity, right? It's used the fact that the universality, right? And this use alignment. So it's not a GIM mechanism. And RS-GIM would be that somehow you get degeneracy. This is not RS-GIM. It's RS flavor suppression. And I don't know who gave this name, but, you know, No, I would never say such thing on Shabbat. Come on, I mean, we are friends. No. You think Shabbat gave it? It's possible? No. Really? I don't know. No, I knew that Gilad used it. Also my friend. I mean, all the people in the field are my friends. So it definitely is one of my friends who did it. You know who did it? Maybe Kaustub? That's a possibility. No? You see? Why did I brought it? Why did I brought it in? Right? Why I just say, let's call the RS-GIM and let's move on. So let me restart. So this mechanism called the RS-GIM mechanism and let's move on. Okay. Any more question on this? Like real question? No? Okay. So these are just examples. I go very, very fast on these examples. But it's a really cool idea. You just, go and do them. It's really cool. You saw some Bessel functions. Bessel functions are not only there for electromagnetism. It's really nice, I want to talk now about one other model, and that's the idea of MFV. And the idea of MFV is basically, it's not a model. It's more of an idea, okay? And the idea of MFV is, again, another kind of manifestation of the alignment mechanism. So what is the idea of MFV? The idea of MFV is as following. We make the assumption that the flavor symmetry is actually a good symmetry that is spontaneously broken at some very high scale. Okay? And once you make this assumption, it's very different than I say there's no symmetry at all. I want you to see the difference. If I just have, I said, I have an approximate symmetry, the U3 cubed of the standard model, then when I put new physics, I should write everything that I can. However, if I have a symmetry that is broken by some very specific mechanism, I should write only the things that are invariant, and then I know how they are broken. Okay? That's the same idea that we have in the standard model. In the standard model, we can say, I just don't have SU2 cross U1. I only have U1 electromagnetism. And then I will have a much, much bigger Lagrangian than I have when SU2 cross U1 is broken spontaneously. Right? So now we make the following assumption, that actually flavor is a good symmetry, and is broken somehow at some high scale, but some field that requires a VEV. Okay? And it's not only one field that requires a VEV, it's actually quite a lot of fields that require a VEV. And those fields usually go under the name of flavons. Why flavons? Because they are related to flavors, right? So those flavons are some fields that require a VEV, and they require the VEV such that at the end of the day, they generate the Yukawa matrices. And making the assumption that they are the only field that break flavor, that means that no matter everything that we write in our model, all the flavor violation must be proportional to the Yukawa matrices. Okay? So you can just say, I want all my flavor violation to be in the Yukawa. And you can say, well, I know why it is. I want it to be part of the Yukawa because it is a spontaneously breaking theory, and therefore that's the only thing that I can write that must be proportional to the Yukawa. Okay? And why this is helping us? It's helping us because the Yukawa, to some degree, is very, very small. Let's think only about the down Yukawa, where clearly everything is small, right? The down Yukawa is small, and therefore, if everything is proportional to the down Yukawa, I'm going to get very small numbers, okay? So for example, if I assume MFV in SUSY, and I write the mass of the squarks, the mass squared of the squarks, let's do it to the down squarks, right? Then I just write everything that I can write, assuming that I have the full symmetry, and I treat the Yukawa as spurions, okay? So I can write something like y plus y dege y plus, but I neglect those because y is a small thing, right? So then I see how I get this universality automatically. Because I start with something that is universal, because I can write it, because it's symmetric under flavor. And this one is also symmetric under flavor, but it's break the flavor after the flavon requires a wave. But these waves are very, very small, right? Because the bottom Yukawa is 10 to the minus 2, and I have here this squared. So I get correction of order 10 to the minus 4, which are very, very small. And therefore, I can actually get very, very good universality. And this universality is good enough to solve not to have problem with these bounds. Okay? Was it clear? I was a little rushing here. Yes? Was it clear to those who never heard about it before? Because I know many of you heard about it before. So then it's like, I think it's called preaching for the choir. That's how you call it? Yeah. So Yeah. So there's quite a lot of UV completions that exist for this kind of thing. And the idea is this. You just put many, many scalar fields, and all these scalar fields requires a wave. And of course, we don't ask why those waves have these hierarchies. But once those waves have a hierarchy, then you can get these kind of things. Okay? And in practice, at the low energy, at the infrared, what we are doing, we basically just assume that we should write everything just as powers of Yukawa matrices, and then we are done. The problem is that the top Yukawa is not very small, and if the top Yukawa is not very small, you cannot neglect higher order term. And if you cannot neglect higher order term, at the end of the day, you can write everything. Okay, so what are you doing? So, okay, at least then you play the usual game. You say, well, the strongest bound comes from the down sector anyway, so let me write this kind of the down sector, and you can play other games, and you can use this idea in many other places. Yes, this is dimensionless number. So,
how do we get these from that?
So you just have. Sorry.
Some kind of ratio.
So these ones. Oh, why the waves? Oh yeah. So at the end of the day, is the usual story is that you get some wave of some particles, and then you have some mediation to the standard model, and those mediations done by some other heavy guys, and those numbers are basically the wave of those scalar fields over some mass of some fermion that is the mediator, and you generate something like this. Okay? Good. I have like 7 minutes, so I want to do one last thing that I was planning for today. And so what I did so far, basically I just very, very briefly, really briefly, I gave you an idea how when you do model building, with the idea to try to solve the hierarchy problem, what kind of tools do you have in order to avoid the flavor bounds? And what we find is basically you have to use this kind of combination. And again, any model on the market that you open, there's like so many model buildings, right? There's so many models out there. All those models use some of those tricks, okay? At the end to kind of get away from model building. So that's what I wanted to talk about this. And in the 5 minutes that I have, I want to be very brief to talk a little bit about the question of the mass of the fermions, okay? And how they are related to what I did so far. So the question of the fermion mass is, we talked about it, it's a technically natural problem. So many times we say we don't care about it. But I was arguing that actually it's, just say, I don't know what the scale that is happening. But let's try to actually work out some models, try to see how it works. And I already give you one example, and that's the example of the Randall Sundrew model, where you put the fermion in the bulk, and you actually can get those mass fermions. And you can do it also with the flat extra dimension. You put the fermion in different location in the extra dimension, and the overlap give you the different masses. So very kind of a cool ideas of how to do this. So what I want to describe to you now is another idea, which I think is, I don't know if this is the oldest idea, but I think it's the oldest idea that I'm aware of that tried to solve this problem before people talked about extra dimension. And let's go under the name of the Frogat-Nielsen mechanism, or the FN mechanism. So I want to explain it very briefly. And actually, when you take the Frogat-Nielsen mechanism, eventually what you get, not only that you explain the mass of the fermion, you also, naturally, you can get some kind of an alignment in supersymmetry. Okay? Just like in Randall Sunroom, when you put the Randall Sunroom in and try to solve why to explain the masses, you also automatically get alignment, and you get some suppression of the flavor bonds. Okay. Yes? Oh, no. I should have write it. Frogat-Nielsen, these guys are Danish physicists, and I mean, the way that it's written, it's not like the way it sounds. Frogat-Nielsen. How do you know that? Oh, okay. That's why I said I cannot. Okay, the Frogat-Nielsen mechanism. And the idea of the Frogat-Nielsen mechanism is the following. And maybe I will not go all the way through, but I want to make the following interesting assumption. And talking about numerical values, from the very start, when people start understanding the number of the CKM, people notice the following really cool result. And the result is as following. If you look at the mass, md over ms, so the mass of the d and the mass of the s are not very well known, but the ratio is much better known from chiral perturbation theory. The best number that you can find is 0.51 plus minus 0.004 for this ratio, okay? And then you ask what is sinus theta Cabibbo, and sinus theta Cabibbo is, to a good approximation, 0.22, okay? Just look at this number and what jump at you immediately? What jump at you immediately? That's true, but that's not what I'm after. Square, right? So if you take this squared, it's this. What is 0.22 squared? It's 0.4, it's 0.0484, which is within 1 sigma, this, right? So actually, you just look at the data and you find this really interesting result that sinus squared theta Cabibbo is equal to md over ms. Okay? And that was an old result. People realized these numerical things long ago. And of course, you can just say, okay, who cares? It's like the fact that the mass of the bee is like the number of feet in a mile, and it's a complete accident. However, when you see something like this, you are going to ask, maybe there's actually a reason for this to happen. Maybe this is not just an accidental numerical things, but it actually comes from some deeper physics that I have into these things. Okay? So that's the game that we are playing. Can we get a model that actually predicts it independent of the exact numerical value that I have? So let's move on to here. And let's play this game. So let's walk, say, in the basis where the up Yukawa is diagonal. And in this basis where the up is diagonal, let's assume that the down Yukawa has the following form: epsilon squared, epsilon, epsilon, and 1. Okay? With some order 1 coefficient in front, if you like. But if you just look into this mass matrix, you ask, this mass matrix, what is the 2 eigenvalues of it? You know how you do 2 by 2, right? You know the trace is 1, and the and the determinant is epsilon squared minus epsilon squared with order 1 in front of it, so it's epsilon squared, right? So looking into... let me slow down. What I'm saying is that the order, these epsilons have order 1 in front of it. So the determinant is epsilon squared, and the trace is 1. So therefore, the 2 eigenvalues are order 1 and order epsilon squared, because the sum of 1 and epsilon squared is 1, and the product is epsilon squared. So just from here, I know that md over ms is of order epsilon squared. right? And then what is the mixing angle of this matrix? In such matrices, the mixing angle is this over the difference, right? That's tangent to theta is this over this. So the mixing angle is roughly epsilon over 1, so the mixing angle is order epsilon, right? So just looking for this, I see that sinus theta Kabibo is order epsilon. Boom. That's what I wanted. So actually, just having such a mass matrix immediately give me this kind of a prediction that MD over MS is equal to sinus square theta. Okay? Sorry?
Say something about MC over MS.
Yeah, so you can say something about MC and MU. So when you play the same game with MC and MU, the mass matrix should have higher powers of epsilons because the ratio of MC and MU are bigger. And then when you play the game, you find that the mixing angle from the C and U is actually much smaller than this mixing angle. And what is the mixing angle in total? The mixing angle in total is the sum of them with some arbitrary phase, right? So when you play the game with the C and the U, you find that the mixing angle is order epsilon squared, okay? And therefore, the total mixing angle is you have some contribution of order epsilon, contribution of order epsilon squared, so it's order epsilon, okay? So I have actually a prediction of this kind of mass matrices, okay? So now the question is, can I get a model building trick in order to get this kind of a mass matrix? Okay? And the answer is, I wanted to say the answer is no, so let's go home. But no, the answer is yes. The answer is actually yes. Yes. So this is somewhat similar to the seesaw mechanism, but in the seesaw mechanism, we really don't care about the mixing angle. We just said it's completely very, very small. Okay? And we set this to 0, and the fact that we have some epsilons here give me this. Okay? Here, I really care about the two of them. So in the seesaw mechanism, I don't care about the heavy guys. Here I do care about both. I do care about the light and the heavy things that come out of this mass matrix. Okay? So I need another 10 minutes. I will not get into the details here. What I just want to say is that this Froggatt-Nielsen mechanism actually is a very well-defined procedure where I impose a symmetry. Usually we impose a U1, or it can be whatever, a Z10 symmetry or some Zn, or a U1 symmetry. And I assume that they have some scalar field that acquires a wave and breaks this symmetry. And I actually can generate this kind of mass matrices. Not only that I can generate this mass matrix for the 2x2, I can actually generate it for the 3x3. And when I do generate them for the 3x3, I find really interesting result that I have 9 numbers that I can fit, which are the 6 masses and the 3 mixing angles. And I made it out with 8 parameters. So it doesn't sound like a big deal, but it is a big deal. Because if you have 8 parameters that predict 9 numbers, you have one non-trivial prediction of such a framework. Okay? And then you just play the game and you look at the data, and this prediction is just good on the money. Okay? So it's post-prediction because the model was done after the data was out, but it still is the fact that there's actually kind of an idea of how to explain mass matrices based on symmetries. Okay? And then you can take these ideas and you can apply it to supersymmetry. You take these charges and you apply them to supersymmetry, and what you find that you get alignment. Okay? The same idea. You get alignment naturally. Because the fermions and the scalars both have the same horizontal charge, the same charge under this new U1 symmetry. Okay? So again, I will not go into this. It will take me another 15 minutes. I just wanted to kind of mention this idea that there are some model building that actually, when we try to solve the mass fermion mechanism, we also kind of use it in order to solve this by using alignment. So that's all I wanted to say about new physics. What I have in my last lecture tomorrow, I want to talk about measurements and how we get a little bit of kind of dirty measurements, how we actually measure CP violation. So that's all for today.